Hello everyone and welcome to part 3 of the course. In this part we are covering in great detail the smoke management systems of the atrium enclosures. And atriums, as we can see on the figure on the right side of the screen, are a large volume enclosure that is open to multiple one or more floors, and it requires a sensitive engineering analysis and a great deal of care while designing the smoke management system to prevent the smoke spread from spreading into these floors that are open to the atrium, or smoke to overfill the atrium. So in this chapter we are going to discuss the basic definitions of the atrium and related common spaces in accordance with the international codes and standards to give you the correct definition of the atrium and when this volume can be used and called an atrium and when it's not. And after this we are going to discuss the atrium fire scenarios, the potential fire scenarios, locations and naming for the atrium space. After this we are going to discuss in detail the smoke control or the smoke management approaches of the atrium enclosure. And after this I'm going to give you a brief introduction into the airflow method, which is used for protection of the communicating spaces that are usually a place which is open to the atrium enclosure. If we refer to the paragraph on the left side of the screen, which is quoted from NFPA 101, the Life Safety Code, this paragraph is defining what is meant by an atrium. So in this paragraph, which is referenced with the reference number of 8.6.7, defining the atrium as atrium is a separated space from the adjacent spaces by fire barrier with not less than 1 hour fire resistance rating, with opening protectives for the corridor walls unless one of the following is met. So the following is on the paragraph on the right side of the screen, starting by A, B and C. Paragraph A is that the requirement of 8.6.7, which is this paragraph we are discussing, shall not apply to the existing previously approved atriums, which means that if the building is existing building, the conditions will be different if the building is new building. Paragraph B states that any number of levels of the building shall be permitted to be opened directly to the atrium without enclosure, based on the results of the engineering analysis required in this section. And paragraph C, glass walls and inoperable windows shall be permitted in lieu of the fire barriers where all of the following are met. And by the following I mean items 1, 2, 3, 4. Item number 1, which is automatic sprinklers, are spaced along both sides of the glass wall and the inoperable windows at intervals not exceeding 6 feet or 1.8 meter. The automatic sprinklers are specified and located at a distance from the glass wall not exceeding 12 inch or 30 cm and arranged so that the entire surface of the glass is wet upon operation of the sprinklers. Item number 3, which is the glass wall, is of tempered, wired and laminated or ceramic glass held in place by a retention system that allows the glass framing system to deflect without breaking in case of loading the glass before the sprinklers operate. Item number 4 is that the automatic sprinklers required by this section are not required on the atrium side of the glass wall and the inoperable window where there is no walkway or other floor area on the atrium side above the main floor level. So basically the atrium is a volume enclosure that is open vertically into multiple floors, and this enclosure should have protection on the common shared floors. These common shared floors can be seen clearly on malls and on office buildings, where you can see an atrium enclosure with a glass partition, and the corridors in these floors are open to the atrium, or there is a lobby around the atrium which is open to the atrium. So this lobby should be protected by the terms explained in this definition from NFPA 101. NFPA 101 continues to define other space that is commonly found near the atrium, which is a communicating space. Communicating space is the space that is usually open to the atrium. And if we read paragraph 8.6.6, we can see the definition of a communicating space is that the communicating space does not connect more than 3 continuous stories or 3 continuous floors. This means that any space that connects 3 floors maximum can be called a communicating space, and it is not an atrium. It's like a mini atrium, but it's not atrium. Item number 2, which is that the lowest or next to lowest story within the communicating space is a street floor. This is the second condition to have this vertical volume enclosure defined as a communicating space, which is to have the lowest or next to lowest story within this communicating space as a street floor. The third requirement, which is that the entire floor area of the communicating space shall comply with one of the following. The first compliance required is that the area is open and unobstructed, such that a fire in any part of the communicating space will be readily obvious to the occupants of the space prior to the time it becomes an occupant hazard. And the second requirement is that the area is open and provided with automatic sprinklers and automatic detection in accordance with section 9.6. So the fourth definition of the communicating space, or the fourth condition, is that the communicating space is separated from the remaining of the building by fire barriers with not less than 1 hour fire resistance rating unless one of the following is met. And these followings are A and B, points A and B on the right side of the screen. Point A is stating that in buildings protected throughout by an approved automatic sprinkler system, the smoke barrier in accordance with section 8.5 shall be permitted to serve as the separation required. And secondly, point B, which is the requirement of this section, shall not apply to fully sprinklered residential housing units of detention and correctional occupancies in accordance with these following sections. So it's clear now that the atrium is a large vertical volume enclosure that connects more than 3 floors or more than 3 stories high. However, the communicating space is limited to only 3 stories high. Let's continue with our definition, but this time we will refer to NFPA 92 for definitions on the atrium and communicating space. Atrium is defined in paragraph A.3.3.28. So atrium is defined in this paragraph as a large volume space that is uncompartmented space, generally 2 or more stories high, within which the smoke from a fire is either in the space or in the communicating space can move and accumulate without restriction. Atria and covered concourses are examples of large volume spaces. If we followed up to the next paragraph, which is paragraph number 3.3.21.1, this paragraph is defining the communicating space. Communicating space is the space within a building that has an open pathway to a large volume space, such that smoke from a fire, either in the communicating space or in the large volume space, can move from one to another without restriction. These are the definitions of the atrium and communicating space in accordance with NFPA 92, which is the standard for smoke control systems. Following up to the last definition, which is the definition of the large volume space. Definition of the large volume space can be found in paragraph 3.3.21.2, which states that the large volume space is an uncompartmented space that is generally 2 or more stories in height, within which the smoke from a fire, either in the space or in a communicating space, can move and accumulate without restriction. So what does this mean? To simplify this, we need to look at the figure on the top right side of the screen. The atria is a large volume space that share more than 2 or 3 stories high, continuously open without any obstructions. So in the event of a fire, the smoke will accumulate on the high level of this enclosure. However, the communicating space is the space that has up to maximum of 2 to 3 stories high in height, not more than this. So if we refer to the figure on the bottom right side of the screen, we can see the volume enclosure shaded by blue is the communicating space, because it's a space that is open for only 2 stories high. However, on the top right side of the screen, this shape has both the atrium and the communicating space. Atrium is a single large volume space that is open vertically to more than 2 or 3 stories high. And this is the difference between the atrium and the communicating space in accordance with the NFPA 92, which is the standard for smoke control systems. Fire inside an atrium can be occurring in 4 potential locations, and these 4 locations are described in accordance with the bloom shape or the bloom behavior. And by bloom, I mean the bloom of smoke which is rising from the fire to the high level. So the fire location and bloom type can be specified into 4 categories. The first one, which is the fire scenario that is happening in the middle of the atrium, and this is known as the axisymmetric bloom. And the second location is the wall and corner bloom. And the third location is in communicating spaces, what's known as the balcony spill bloom. And the fourth location, which is in a space open to the atrium, which is known as the window bloom. So axisymmetric bloom fires are formed usually from the fires that are involving fuel packages remote from any walls in the atrium, which is usually near the center or at the center of the atrium floor. Being remote from any walls, then we need to note that the air is entrained usually around all of the bloom perimeter of the smoke along the entire clear height of the bloom. And of course, more entrained air means more mass flow rate required to extract the smoke. While the wall and corner bloom fires are usually located near either walls or corners, and they principally entrain the air only along the surface of the bloom, which is away from the walls or corners. That's why, as a result, the amount of smoke production is relatively reduced due to the reduction in the entrainment air effect, in comparison, of course, to the axisymmetric bloom, which is remote from any walls and entrain air from all around the perimeter of the bloom. The third fire location is the balcony spill bloom. A balcony spill bloom is generated in cases where the smoke reaches an intermediate obstruction, such as a balcony that horizontally travels under the obstruction, and then it turns and rises vertically upward to the void of the atrium enclosure. Scenarios where the balcony spill blooms involve smoke rising above a fire, reaching a ceiling, a balcony, or any other significant horizontal projection. After this, it starts to travel horizontally towards the edge of the balcony. And the characteristics of the resulting balcony spill bloom, it depends mainly on the characteristics of the fire and the width of the spill bloom. Also the height of the ceiling above the fire. And if there are any draft curtains that are contained on the balcony spill bloom where the fire is proposed to happen. Because draft curtains contain the fire spread horizontally when it exits the room or exits the place that have a fire. The last fire location or the last fire scenario, which is in a space open to the atrium, or what's commonly known as the window bloom. In the window bloom, the room that is having the fire origin is usually fully involved in a fire, and there are no horizontal obstructions like windows or balconies that can cause the scenario of balcony spill. So the room is open to the atrium directly, and the above floors are completely isolated from the atrium. There are no balconies or open lobbies or corridors. So the bloom rising will be like commonly known as the window bloom. When it comes to the atrium smoke control approaches, there are four commonly known approaches. The first approach, which is the smoke filling, and smoke filling is utilized by adding a reservoir above the atrium volume, and this reservoir acts like a smoke filling reservoir. This is designed carefully by the architect and the life safety engineer to allow that the reservoir filling time with the smoke is more than the evacuation time, which means that if the occupants will evacuate the building in 1 minute, this means that the reservoir filling time should be more than 1 minute, so that it allows the occupants to evacuate at least the top floors safely before this reservoir is filled with smoke. The second approach, which is the mechanical exhaust. Mechanical exhaust utilizes the basic concept of equilibrium, which means that for the developed fire, I'm going to utilize a smoke fan or a smoke extract fan that will extract the same amount of airflow that equals the same amount of the actually generated smoke from the fire, which means that the mass flow rate of the fan will equal the mass flow rate of the smoke generated from the fire. And this requires sizing of the ventilation system or the smoke management system in accordance with the actual fire load size. And the third approach, which is the natural smoke heat venting. This is designed and based and utilized in accordance with NFPA 204 and in accordance with the IBC or the International Building Code. The basics behind this concept of design is that instead of using fans to suck the smoke from the high level or the ceiling, you will use natural venting means instead. They are similar to the windows, but they are equipped with automatic detection systems that will detect the heat and the smoke, and once it detects them, it will open automatically to allow venting for the smoke naturally without the need for electrically powered extract fans. And the fourth approach, which is the tenability analysis. Tenability analysis is the performance-based analysis at which you need to ensure that the time required until the smoke layer descend to dangerous levels is more than the evacuation time required. So you will conduct the evacuation analysis, and you will conduct the tenability analysis, and you will compare the results to make sure that the time required to fill the atrium with smoke is more than the time required for evacuation. And this requires fire dynamic simulation, and I have 3 excellent courses that are covering this subject in great detail. Let us cover the atrium smoke control approaches one by one. We're going to start with the smoke filling approach. In the smoke filling approach, in case of a fire incident that happened and ignited a fire in the atrium, the occupants will start to evacuate as the smoke will start to fill in the atrium space in parallel. So my main concern here is that I need the occupants to evacuate safely before the smoke starts to descend to dangerous levels. And this natural smoke filling mostly applies to the very large atrium volume enclosures. In this, like I said, the basic concept is that I need the smoke filling time to be more than the evacuation time. So in this scenario, I need to understand and I need to know that the minimum smoke layer depth is usually recommended to be 20% floor to ceiling height, in accordance with the related international codes and standards. For this scenario, you require a performance-based analysis, and you need to conduct a fire dynamic simulation or manual filling calculation to validate that the filling time will be more than the evacuation time. If we refer to the figure on the right side of the screen, top right side of the screen, which is quoted from ASHRAE, we can see that the bloom rising from the fire is, once it reaches the ceiling, it will cause the ceiling jet to spread horizontally, and it will spread until it hits the wall, and then it will start to drop down and cause circulations, and it will start to fill the smoke, and the smoke will start to flow under the ceiling jet until it fills the atrium gradually. There is a note here which is mentioned by ASHRAE that the minimum smoke layer depth is 20% of the floor to ceiling height. This means that the volume or the enclosure of the smoke filling reservoir should have a minimum depth of 20% of the floor to ceiling height. If we refer to the figure below, which is also quoted from the international codes and standards, there are some notes on the smoke filling approach of the atrium. Note number 1 is stating that if the evacuation time is less than the atrium filling time, an atrium filling system is appropriate. Note number 2, which states that the evacuation time consists of the modeled evacuation time multiplied by the evacuation efficiency plus the time delay in initiating the evacuation. Note number 3 is stating that the atrium filling time is the time in which the smoke layer will start to descend to the critical level above the highest occupied floor. And the second approach, which is using the mechanical extract option or using mechanical smoke exhaust fans to extract the smoke from the atrium at a rate that is equal or more than the rate of smoke production from the fire. And this is crucially important. Also, in this scenario, a fire dynamic simulation or CFD or manual filling calculation is required for the volume enclosure of the atrium. Okay, but what about the makeup of the atrium? Because of course, if I am sucking air or exhausting air from the atrium, I will create a negative pressure. So I need to compensate it with a calculated percentage, which is usually 85% negative pressure. So if I am sucking in 100 CFM, I need to supply 85 CFM to maintain the negative pressure of 85%. So regarding the makeup air fans are often sized at 85 up to 95 of the total exhausted flow. And the exhausted flow, as a reminder, is sized based on the actual generated smoke mass flow rate from the fire. You need also to consider that a balance should be done through the openings and the leakage path, which means that If you have leakage path or open doors or any other openings, you should add this in the balance of the pressurization that you are trying to maintain, which is negative 85 to 95%. You need also to understand that the natural makeup air should have a relatively low velocity, and makeup air is usually provided from openings or from doors that are located at low level. So the makeup air velocity should be 1 meter per second in order to prevent any bloom disruption. By bloom disruption, I mean that circulation will occur between the fresh air and the smoke rising, and it will mix this with that, and it will cause adverse filling of smoke. That's why the fresh air or the makeup air needs to be gentle with a velocity that is 1 meter per second to prevent any bloom disruption. One of the common problems that are encountered in the atrium smoke management, and especially in the mechanical exhaust smoke approach, is the stratified hot air layer. Stratified layer forms when the average bloom temperature of the smoke is less than the hot air layer temperature. Hot air layer temperature we can see on the figure on the right side of the screen, and it is the layer at the top side of the atrium. This layer is affected by solar radiation, and solar radiation usually causes this stratified layer temperature to increase, and sometimes in some scenarios to reach up to 50 degrees Celsius, because this top layer is usually adjacent to a glass, and this glass allows the temperature to increase due to the radiation exposure from the sun. That's why the stratification or the stratified layer can block the smoke from reaching the ceiling, because this stratified layer is hotter than the smoke. That's why it have more buoyancy and it have less density, so it will rise up. If it rises up, it will block the smoke from reaching the ceiling, and it may prevent the activation of some of the detectors or the natural vents that are located on the ceiling of the atrium. And the solution for this is to use beam detector. Beam detector will overcome this problem because the beam detector is not arranged at the ceiling inside the hot layer. It's arranged in tilted positions, as we will see in the following slides. There are three main configurations for the beam detectors to be fixed in an atrium enclosure. In these three arrangements, we will see a plan view and a sectional view for each arrangement. The plan view will give you the view from above or from top, and the section will give you the view from the side. Starting by the first arrangement, which is the upward angled beams to detect the smoke layer. We can see in the plan the beams are arranged in parallel arrangement, but they are upward angled in opposite sides, and this is clear in the section. And if we look at the arrangement number B, or the second arrangement, which is the horizontal beams to detect the smoke layer at various levels, we can see here that the beams are arranged under each other, but there is a spacing between these beams, so they are arranged at the variety of levels. And the third arrangement, which is the horizontal beams to detect the smoke bloom. This means that you will put a set of beams at a specified horizontal level to cover the entire area of the atrium, and they will be spaced, as we can see on the figure on the bottom right side of the screen. The horizontal spacing will be divided in the form of x, and x will be the equal distance between each detector, and the distance between the detector and wall will be x divided over 2. However, the vertical distance will be x will equal b divided over 4, and b will be the elevation of the beams divided over 4. Let us try to understand a very well-known phenomena that adversely affects the performance and the efficiency of the atrium smoke management system, which is called the ploughing. Ploughing is a phenomena that happens when the air below the smoke layer is being pulled to the smoke layer into the smoke exhaust instead of the smoke itself, and this we can see on the figure on the top right side of the screen. In this situation, this occurrence and this suction of the clear or the fresh air instead of the smoke through the fan will lead to a reduction in the exhaust from the exhaust smoke layer, and this will cause the smoke layer to descend and lower and grow bigger, because the fan is not efficiently sucking smoke, but it's sucking normal air. So the solution to this is to increase the number of smoke exhaust points and the distance between each smoke exhaust point to reduce each inlet's flow rate below the maximum value that will cause the blowing to happen. So in summary, blowing is that when you size a fan to suck too much air, and this will cause it not only to suck smoke but it will also suck the fresh air, and this will adversely affect the performance of the smoke management of the atrium. We can see also on the figure on the bottom right side of the screen the effects of the smoke lowering and the smoke depth increasing due to the adverse effect of sucking air instead of sucking smoke due to blowing. Here are some of the system activation factors that are related to the atrium smoke management approaches. So the system needs to activate before the fire reaches the design condition, considering these following factors. The first factor, which is the fire detection time, and the second factor, which is the HVAC, the activation and dampers opening or closing time. The third factor, which is the opening and closing of natural ventilation devices. So in summary, what I'm trying to say here is that you need to take into account the time that will be required for the devices and the equipment to activate and deactivate to follow the control sequence in the event of a fire. For example, the air handling unit, it should have fire dampers that should close. So you need to understand the duration that these dampers will close. The smoke or the beam detectors will take some time to detect the fire. You need also to account into these detection times required. And if you are using a natural heat vent for venting the smoke, you need to understand that it will take it some time to detect the smoke or the presence of smoke and to start operating. Another effect that you need to take into account is the sprinkler operating in atriums. You need to understand that a bloom smoke temperature decreases greatly in high atriums, which can cause the sprinklers a delay activation, or it can sometimes, in some rare occasions, to never activate. Of course, we know that the smoke temperature is relatively high, but the more that the bloom rises into the higher levels, it starts to lose heat through the convection and through the buoyancy effect until it reaches a relatively lower temperature, and this might be seriously dangerous, and it can cause the inactivation or the delayed activation of the sprinklers. And you need also, as a designer, to pay attention to all of this. Natural venting approach for the atrium is simply to add natural vents that, once detecting the smoke accumulation or the smoke presence, they will open and trigger automatically to allow for the smoke to be exhausted naturally, utilizing the buoyancy effect. The purpose of adding the smoke vent is to control the smoke layer descent by either limiting it at a certain predefined level or slow down the descent of the smoke layer to provide enough time for the occupants to evacuate. So, since we are using the buoyancy effect of the hot smoke to rise up and exhaust naturally through the vent, this means that we need also to study the outdoor external ambient conditions, because if the wind are blowing, this will exert a positive pressure on the building, and so will it exert a positive pressure on the smoke vent. And this can be a serious problem in atriums that are specially attached to a tall building and atriums that are very near to a tall building. And to see this, we can refer to the illustration on the bottom right side of the screen. We can see that if wind is blowing on this simple tall building, then the wind will create vortices and circulations that will in turn create pressure drop downward of the flow of the wind, which means that in the direction that is not subject to the flow of the wind, which is the direction on the right side, we will have a pressure drop due to the vortices of the wind blowing onto the building. That's why we need to study and evaluate this carefully, especially in the tall building or in the presence of a tall building. Okay, someone will ask, what about the makeup? The makeup air is usually introduced via the low level because we don't want to disrupt the smoke bloom and we don't want also to mix the smoke bloom with the fresh air. That's why it's always introduced via the lowest floor. So makeup air is generally supplied through open vents or doorways or a combination of both at the lowest level, and we need to ensure that the velocity of the makeup is low enough to prevent any mixing with the bloom, and usually the velocity limit is 1 meter per second or 200 feet per minute. The last approach in the atrium smoke management is the tenability analysis. This means that we need to provide a tenable environment for the occupants until the evacuation is completed. This also means that there is a great need to perform fire dynamic simulation or CFD analysis using PyroSim or equivalent tenability software. And usually the tenability criteria is to check the visibility and to check the temperature and to check the heat exposure and also to check the asphyxiance exposure and the air velocities to ensure that all of these criteria will provide a safe, tenable environment for the occupants to escape. And I have prepared 3 magnificent courses on the tenability analysis and on a software used for fire dynamic simulation and for fire and smoke analysis, and it's called PyroSim. Check them out. When it comes to the spaces that are open to a communicating space or that are open to an atrium, you need to provide protection for these spaces to prevent smoke infiltration from atrium or communicating space into these lobbies or corridors or joined open spaces. And the spaces that are open to an atrium can usually be protected by one of the 2 methods. The first method, which is to apply the compartmentation concept. Compartmentation concept is to apply a smoke barrier that will prevent the smoke from infiltrating. It can be a partial compartment or a full compartment that can open in the detection signal in case of a fire scenario to isolate this corridor completely. And the second method, which is to provide protection using the airflow method. Airflow method is simply you are adding or supplying an air into this corridor to provide a sufficient velocity and a sufficient air displacement that will prevent the smoke from entering this place. And usually the velocity that you should keep the air at is 1 meter per second to prevent the smoke from infiltrating into this common lobby or corridor. Airflow method also can be used in tunnels, corridors, and communicating spaces. And the airflow method is not recommended except when there is a potential for failure or a fuel restriction or fire suppression is evaluated to be an acceptable option. And we can see a representation of the application of the airflow method on the figure on the right side of the screen, at which the air is supplied from the left side in a sufficient manner that it is preventing the smoke from progressing further deep into the lobby or corridor. Here also we can see the application of the airflow method in the protection of the communicating spaces that are open to an atrium or the atrium that is open to corridors. As we can see on the figure on the left side of the screen, we can see the air is being supplied to the communicating spaces, which is located at the top floor that is open to an atrium, and it is supplied with a sufficient air velocity and sufficient airflow that it is preventing the smoke to infiltrate into this communicating space. We can see the opposite as well on the figure on the right side of the screen. The air is being supplied at the large volume space, whether if it's an atrium or a communicating space, in case of a fire that is happening in the corridor or the communicating space. And the air is being supplied from the atrium into the communicating space with sufficient velocity that it is controlling the smoke spread and minimizing or preventing it from spreading into the large volume space. If we refer to the figure on the left side of the screen, we can see a figure that is linking the amount of heat generated from the fire with the velocity that you need to supply the air with into this corridor to prevent any smoke infiltration. We can see on the horizontal axis the heat release rate in the British unit, on the below axis and on the top horizontal axis the heat release rate is in megawatt. While we can see on the vertical axis the velocity of the air that you need to supply to minimize or prevent any smoke infiltration and to provide protection for the communicating space. While the tilted lines or the curved lines are representing the corridor width. So let's give an example for this. If we refer to the corridor width curve of 3 feet, which is 0.91 meter, if I want to provide a protection for a fire that have a 0.4 megawatt on the horizontal axis, then I need to go to the velocity of the air that is being supplied of 400 feet per minute or 2 meters per second, which means that if I need to quantify the amount of airflow, I need to multiply the corridor area multiplied by the velocity I just chosen from this curve, which is 2 meters per second multiplied by the corridor area. It will give me the amount of the airflow that I need to supply to sustain a sufficient velocity and airflow rate that will minimize and prevent any smoke spread. If we refer to figure 6.2, which is on the top right side of the screen, we can see the phenomena that is known as the smoke backflow. Smoke backflow happens against the flow of air at low velocities through an open boundary of a doorway through a corridor. And this is the phenomena that will happen if you did not supply air with sufficient velocity. And to prevent this, you need to supply air with sufficient velocity as we have explained on the figure on the bottom left side of the screen. And as a scenario of the successful supply of critical velocity that will prevent any smoke spread, we can refer to figure 6.3. This figure is showing the high air velocity through an open doorway, and it is preventing the smoke backflow and the smoke spread deeper into the corridor or the common communicating space. Hello everyone, and welcome to the example on the Atrium Smoke Management calculation sizing. So in this example, I'm going to use an Excel sheet that is prepared by Ashri, and it is titled as Smoke Calculator, which is used for the Atrium Smoke Control calculations. And this calculator is available on Ashri's website, and of course it's not for free. However, one of the core values in this course is that I'm offering the high valuable resources and for free to all the subscribers in the course. So if we open the Excel sheet together, we will find the first or the main page of the Excel sheet, and it is showing the title of the Excel sheet, which is Atrium Smoke Control Calculator. There are some main tabs here that you can use during the calculation, but the first glimpse shows you that there is two type of calculation for each of the options, which is the first one is the IB units or the British units, and the second, which is the SI units. So you can calculate both of the Atrium calculations using both of these units. First of all, you will find 5 options. The first option is the smoke exhaust to the axisymmetric bloom, and this is the first type of Atrium fires as we have explained. And the second option in the IB units is the smoke exhaust to the balcony spell bloom. And the third type, which is the smoke exhaust with the window bloom. And number 4, you will find the calculations required to prevent the plowing, and we have explained what is meant by the plowing. Number 5 of the IP units, which is the airflow to control the smoke or the airflow method. And the same option will be found on the SI units. However, if you refer to the tabs below, these tabs are the available options or the available 10 options that are presented here. If you click on these options, they will guide you automatically to this designated page. So there is also an instruction to use it here and general information for the Atrium calculation. It is stating some technical information that you need to be aware of, and there is also some QA or questions and answers that can be found here for greater insights on the technicalities related to the usage of this Excel sheet. After this, we are going to enter the pages where you are going to start the calculation of the required mass flow rate for the smoke to be extracted from the atrium. And this in the example of the axisymmetric bloom, which is the fire in the middle of the atrium. And here are the given equations and the notes that are related to the usage of this Excel sheet. You can see here the notes stating note number 1, makeup air is shown as being supplied by an opening or openings to the outside, but it can also be supplied via mechanical fans. Note 2, for calculating the volumetric flow rate, smoke exhaust, a value of Ks is equal to 1 needs to be used, except when another value of Ks is supported by test data or engineered analysis. Note number 3 is for smoke control design, a value of X equals 0.7 is almost always used, and other values should be supported by engineering analysis. We can see the inputs are highlighted here in the form of equations, and these are the input slots, and these are the output slots. And these are the legends of the items that are used in the equations and the factors used in the equation. These are the sequence of the equations that are being used and the conditions related to them. First of all, you calculate the heat release, and then you calculate the Z, which is the distance from the base of the fire to the smoke distance, and it is designated as Z in here. After this, you will, according to the Z height, you will calculate the mass flow rate of the smoke generated from the fire. After this, you will calculate the temperature of the smoke, and this is in order to calculate the density of the smoke, because the density will affect the volumetric flow rate. And lastly, you will take the density that you have calculated and the mass flow that you have calculated from equation 3 and 4, and you will get the volumetric flow rate. This is a simplification of the calculations as obtained from ASHRAE or a related NFPA. So first of all, you will start by inputting the size of the fire, and this is in the British units. So I'm going to use the SI units for simplification. It's the same tab, but the units are modified. So in the event of using a fire in an atrium, usually the size of the fire is 5 megawatts. So the input of the fire, or the Q, will be used as total heat release rate of the fire will be 5000 kilowatt. After you input this value, you will specify what is the Z value that you require. And the Z value, you can refer to it in the legends here. Z is the distance from the base of the fire to the smoke layer interface. So I need this Z to be 1.83 meter, or of course any designer have a different and special design scenario, so you can modify it, but I'm going to assume it will be 1.83 meter. Okay, after this I'm going to enter the ambient temperature of the air. TO, you can find it here, defined as the ambient or outdoor temperature. So this is the ambient of the air that is being supplied as the makeup air from the side here. I'm going to define it as the temperature in the high, hot and humid areas in the Gulf, which is 46. After this, the pressure at the ambient conditions will be remaining same. You can modify it if required, but I will keep it same. And then KZ, in order to define it, you need to see note number 2 above, which is stating here that for calculating the volumetric smoke flow rate of the exhaust, the value of 1 needs to be used. So we're going to keep it 1. After this, I'm going to define the value of x, and the value of x is defined here to be 0.7. As a result of this, once you define all these inputs, you will note that the outputs are defined here automatically and calculated automatically. You can see the QC is referring to the convective portion of the heat release rate, and it is defined in the legend here. So if you enter a total value of 5 megawatt, you will have a convection related heat release rate of 3.5. As a result, it is going to be used in the equation of defining Z1, which is equation here. And then it calculated Z1, which is the limiting elevation. And Z1 is specified here as the flame height. After the Excel sheet have calculated Z1, it will automatically calculate the mass flow rate of the smoke to be 7.84 kilogram per second, and this is based on these equations. For these terms, if Z is more than Z1, you will use this equation. If the opposite is true, you will use this equation. After this, the software will calculate the temperature of the smoke, and in our case, it will be 492.7 degrees Celsius. After this, it will calculate the density of the smoke, and you can see here that the density of the smoke is half the density of the air. And this will affect greatly the mass flow rate. As you can see that the resultant volumetric flow rate will be relatively high, and this is the correct way to calculate the mass flow rate required for the exhaust system of the Atrium. This means that we need a fan that will achieve a minimum smoke exhaust flow rate of 17 cubic meter per second. After this, the second step, which will be to define the plowing requirement, and the plowing is to define the proper spacing between each of the smoke extract grills to prevent the achievement or the occasion of the plowing phenomenon. So this is a plowing in IB, and this is a plowing in SI. I will use the plowing in SI. And here are some notes regarding the plowing. Note number 1 is stating that for a ceiling mounted exhaust inlet, L should be smaller than 2D and the gamma should be 0.5. So these are the notes that are being used in the input of these calculations. In these calculations, you will follow the same steps, defining the heat release rate, which is in our case 5 megawatt, defining the temperature of the ambient, which is 46, and defining M, which is the mass flow rate of the smoke, and this value you will take it from the axisymmetric bloom of 7.84. This is the value we specified. So I will take it and put it here in the value of the mass flow rate of the smoke, which is 7.85. By the way, there is calculation for the rectangular grill and for the round grill, and both of the calculations have slightly different equations. So you should choose based on the availability of the air outlets you are using. After this, you are going to specify the volumetric flow rate of the mass of the smoke, and this we have calculated from the previous tab of the axisymmetric fire, and this is the volume, which is 17 cubic meter. So I'm going to use it here, update it as 17, and then I'm going to use the D. D is the dimension of the grill. D are dimension related factors. D is the minimum depth between the bottom of the grill and the maximum smoke layer depth. So I'm going to assume it based on the smoke layer height that I need, meaning that in my occasion I need the smoke layer height value of Z, which means that the smoke will not descend below 1.83. So by knowing this value of Z, I will locate the grill at the high ceiling mounted area, so I can subtract the value of 1.83 minus the BOD of the grill, and it will give me automatically what is the value of D. I'm going to assume it will be 2.77. After this, the value of gamma, you can find it from the notes in here. After this, the value of k, you can find it from note 7. After this, I'm going to give the dimension or the proposed dimension of my grills that I'm using, and it will calculate what is the minimum separation required to prevent the plowing. So A is, as seen here, it's the length of the grill, and B is the width of the height of the grill, and this is 1.2 meter by 0.75 meter, and this is the number of the air outlets, and this is the area of R, and area R, you can see it in the legend here, and it is defined as, in the absence data, 0.5 is suggested. Okay, so area R is the ratio of the free area to the total grill area, which means that due to the blockage of the blades of the grill, there is an area ratio. So this value of 0.5 is highly suggested. After you finish filling all these data, you will get the results in here. The smoke temperature will be calculated, and the maximum volumetric flow rate of the smoke will be calculated. And this is VE. VE is stated here as the volumetric flow rate of one exhaust inlet. So this will be for the single grill. It will carry 2.83 cubic meter per second. And S minimum is the minimum separation distance. You can find it also in here, in here. S minimum is the minimum edge to edge separation between two inlets. And DI, you can find it also here, the effective diameter of the inlet. And D divided over DI, you will find DI, which is the effective diameter of the inlet, and D, which is the depth of the smoke layer below the lowest point. So these are the dimension related data that you should follow to prevent the plowing. It will give you the spacing between each two grills and the separation between the grill and the